Esteemed viewers, in this tutorial video, we will elaborate a famous algorithm by Warshall, namely Warshall's algorithm, which is directed towards finding the transitive closure of a graph. By finding transitive closure of a graph, we seek to answer very important questions on a directed graph which is specifically meant for transportation connectivity or some kind of a connectivity issues in any domain, as a matter of fact. For example, in a directed graph meant to represent some kind of a transportation planning, that means connectivity between different vertices of a connected graph, directed graph, we can answer questions like, is there a direct flight from airport X to airport Y? Airport X and airport Y being the vertices of a directed graph. Is it possible to fly from X to Y in one or more flights with an intermediary station in between? Is city A connected to city F? If it is connected, how many stations are there in between? Are there any 3 stations or 4 stations? Therefore, how many intermediate cities are in between? And it will also count the number of paths that exist between any 2 vertices selected at random. Therefore, transitive closure will try to find out some kind of a connectivity between any 2 vertices selected at random. It is not a trivial connection like direct connection. It is a non-trivial connection. Okay, and transitive closure will also establish some kind of a transitive relationship between 3 vertices or 3 cities or 3 values and whatever the vertices of a directed graph is modeled about. Okay, transitive closure will take a input of vertices something like this. This is a trivial connection. Let us say this is vertex A and this is vertex B. Okay, this is vertex A and this is vertex B. We will sketch that. This is vertex A and this is vertex B. So from the adjacency matrix, this is visible. That's all. A to B is connected, B to C is connected, C to D is connected, D to E is connected. Okay, this is what an adjacency matrix would say. And if you find out the transitive closure of such a graph or such a connectivity, it will tell us whether there exists a connectivity between A to C. It is some kind of a relationship that exists. Okay, if graph were to be called as a relationship between any 2 vertices selected at random, the relationship being whether it is connected or not. If it is connected, we are going to take it as 1. If it is not connected, it will be taken as 0. Therefore, adjacency matrix of a graph is a Boolean matrix. So also the transitive closure of a graph is also a Boolean matrix. But this Boolean matrix has volumes to say about 2 vertices and its connectivity or reachability. Is E reachable from A? It should not be a trivial connection, direct connection. It should be a non-trivial connection. Or it will also answer questions like, after starting from A, is it possible to come back to A? If it is so, how many stations are involved? How many intermediate stations are involved? These type of questions are answered. Questions could be answered by just a Boolean matrix. Boolean matrix developed using adjacency matrix of a graph. Directed graph. Of course, one primary condition is in order to find out transitive closure of a graph, the graph should be directed. It could be cyclic or it could be acyclic also. Okay, and by the by, our viewers, respected viewers, should be knowing there exists as a kind of a relationship called as equivalent relation among the same family of entities. Equivalent relation. Okay, in that, in order to establish equivalent relationship among any 2 entities or any entities present in a domain or proper entities present in a point of specific interest, okay, the 3 conditions should be satisfied. One is reflexivity, other one is symmetry, and the next one is transitivity. Okay, it is something like this. If a node is, with respect to the graph, if a node A is connected to itself by means of a self loop, something like this, then it enjoys the property of reflexivity. If there is another station like B, let us say, if AB is connected, A to B, there is a connection between A to B, and if exists a connection between B to A, then it satisfies the symmetric condition. A to B is connected and B to A is also connected. And if we have one more station, let us say C, if A to B is connected, B to C is connected, then it also means C to A is also connected. Okay, this is symmetry, this is symmetry, and telling if A is connected to B and B is connected to C, C is also connected to A, then that is the case of transitivity. And we seek to find, we never search for equivalent relation in case of directed graphs. As far as transitive closure is concerned, we try to seek, we try to find is there any existence of a transitive condition between, transitive relationship between any two vertices selected at random, of course with some intermediate vertices in between. Okay, this is an excellent, finding transitive closure of a graph has an excellent applications in real world, and we will just talk about it at the end of this video, end of this discussion. Okay, currently we will just concentrate on the what exactly the algorithm has to say and how exactly we can obtain the transitive closure of a graph, right? And of course this particular question of interest is dealt under the ambit of dynamic programming strategy. Okay, this is dynamic. Transitive closure is built for a graph on a overlapping solutions way. Okay, we will have the starting solution, that is adjacency matrix, and the solution is solution of transitive closure is built progressively one after the other, right? Now, okay, first of all we will define as to what transitive closure is. Transitive closure of a directed graph with n vertices is nothing but n by n Boolean matrix, that's all. So transitive closure, like adjacency matrix, is also a Boolean matrix n by n, where n is the number of vertices present in the directed graph, and this is represented by T, naturally, obviously. Okay, if this is the transitive closure and every element Tij, small Tij, in which the element has an entry 1, if an element Tij in a transitive closure graph has an entry 1, if and only if the ith vertex and the jth vertex are connected by non-trivial paths of arbitrary lengths. Okay, non-trivial paths of arbitrary lengths. If A to B is connected, then there should be some other intermediate vertices which will be connecting, which should be not more than n, where n is number of vertices in the graph. Otherwise, if there is no such paths exist between any two vertices, that is ith vertex and jth vertex, then the entry that is made in this transitive closure is equal to 0. Okay, this is unlike adjacency matrix, wherein transitive closure as a matrix, as a Boolean matrix, is to be obtained in a step-by-step manner, progressively, by making use of the previous solution that is gotten. Okay, anyway, first solution is, okay, this algorithm starts from the adjacency matrix. Adjacency matrix will give at least some kind of a clue regarding direct connection between two vertices. So Warshall's algorithm constructs the transitive closure of a graph progressively. It develops starting from the adjacency matrix of the graph. Here it is. It will start. This is the adjacency matrix, of course. T naught is the adjacency matrix. T is a notation to represent a transitive closure. So T naught, from making use of T naught, T1 is built. Similarly, a Tk is built by using Tk minus 1, and T of n is built making use of T of n minus 1, where n is number of vertices. Therefore, this particular algorithm runs exactly n number of times. Okay, so transitive closure algorithm makes transitive closure algorithm proposed by Warshall makes n number of iterations starting from the starting adjacency matrix. So initially it is going to initiate the transitive closure 0th, okay, transitive closure, the starting transitive closure matrix to be A. This is how it's going to build. Okay, the TK transitive closure, the kth transitive closure is built making use of k minus 1th transitive closure or k minus 1th matrix. So in k minus 1th matrix, the kth row and kth column is selected. If k minus 1th matrix is 1, let us say, then in order to build the t to the power of 2 or t2, the transitive closure in its progression, we are going to select the second row and the second column. Okay, therefore in k minus 1th matrix, therefore this will give a solution. Okay, so if we select kth row and kth column, and if this is ith row and jth column, if there is one already present in tk minus 1 over here, that is what is that, ith row and jth column of a k minus 1th matrix happens to be 0, happens to be 1, it will be retained as 1. If it is 0, it will be made 1. It will be made 1. It will be transformed into 1. If and only if there exists 1 in kth row and jth column and ith row and kth column of k minus 1th matrix. This is how I repeat, if at all any entry in the k minus 1th matrix is 1, it will be retained as it is. If at all it is 0, it will be made 1 if and only if there exists 1 in kth row and jth column of k minus 1 and kth column and jth row and ith row of this thing. The intersection of these axes, and if it is 0 and if it is 1 over here and 1 over here, it will be made as 1. It will be turned into 1. Okay, we will take an example and we will just illustrate as to how this particular algorithm really works and how easy it is. And we will also interpret at the end what exactly this transitive closure really means. Okay, now the governing principle of this algorithm is just this: the Tij, okay, the entry Tij, ith row and jth column entry in the kth matrix will be remaining as 1 if at all it is 1 in k minus 1th matrix, or it will be T of ik k minus 1, okay, ith row and kth column of k minus 1 and kth row and jth column of k minus 1, and means it is 1. If this is 1 and this is 1, then only it will become 1, and if it is 0 over here, it will be made as 1, because this is 0 in the earlier matrix, and if this turns out to be 1, this will be selected. Okay, if an element Tij is 1 in T of k minus 1, it remains 1 in T of k. If an element T of ij is 0 in T of k minus 1, it will be made as 1 if and only if Tik, the entry at T ith row and kth column and kth row and jth column are both 1s in T k minus 1. Okay, this is the governing rule, and we need to remember this before whenever we want to develop a code for this. Okay, anyway, we will take an example. So this is a 5 vertex directed matrix. There are 5 vertices, therefore algorithm has to run at least 5 times before it comes out of the transitive closure. Okay, it's a directed connection. It could be cyclic or it could be acyclic. Okay, that is immaterial. So we start with the adjacency matrix. We will write A, B, C, D, E, A, B, C, D, E along the row. A and A is not connected, therefore 0. A and B is connected, it is 1. A and C is not connected directly. So this is adjacency matrix. We know this. We will get this entry, right? So this remains to be the k minus 1th matrix for the development of kth matrix. So this is 0 and 1 is to be developed now. So okay, in order to develop this 1 progressively, we need to select the first row, that is the kth row. kth row and kth column. This is the kth matrix, therefore kth row and kth column. Here there is 1 over here, there is 1 over here. From this one you draw a horizontal line, dotted line. From this one you draw vertical line. Okay, wherever it intersects, wherever it intersects. So here it intersects over here. It's only one location it intersects. Here also it intersects, but anyway there is no horizontal line over here. Okay, so this is the corner. This is ith row, kth column. This is jth column, kth row. Okay, so first row, first column. So k value is 1, 1. Okay, so here there is already 1, therefore there is no question of changing. Therefore in T1, T0 remains as it is. So here is 1. Now in T1 we will select the second row and second column, because T2 happens to be the K, 2 happens to be the K. It should be developed by making use of T1. So we select second row and second column. Wherever ones are there in this column, we will draw a horizontal line in order to find intersecting elements. And here also we can draw a horizontal line, and here we can draw a vertical line. In order to choose the jth column, here in order to choose the ith row, that's all. So here there is an intersecting 0, here is 1 and here is 1. So this will be made as 1, and here again there is 1 coming in this direction, horizontal direction, and here there is a vertical direction. We will just prolong this. The intersection point happens to be 0. Therefore this should be made as 1 and this should be made as 1. Therefore in T2 we can find changes as far as these entries are concerned. This will become 1 and this will become 1. Earlier they were zeros. So it is carried forward. T2 is something like this. Okay, this is 1 is transferred over here and this one is also transferred over here. Since we need to build the T3, we need to select third row and third column. So K becomes equal to 3. So this is third row and this is third column. So here there is 1, 1, 1, and we will draw horizontal lines, okay, from that column. And here we have only 1 on this vertical line. Therefore the intersecting points are this one, earlier it is 0, this one, that is also 0. So it comes from 1, it comes from 1 vertically, it comes from 1 horizontally. Therefore this intersecting point should also be made 1, and this intersecting entry should also be made 1. Therefore in this matrix also there are 2 changes. Here there is 1 and here there is 1. Here there is 1, 1 and 1. There are 3 changes over here. So 1 was there earlier, 1. Okay, 3 changes are modified and it is carried forward. Now in T3 we need to select 4th row and 4th column. Here there are going to be many changes because there are many ones. Here we draw 1, 2, 3 vertical lines, and here we will draw 3 horizontal lines, and this is an intersecting point. This will become 1, and this is an intersecting point. This will also become 1. This will also become 1 because it is intersecting point. And here also this will become 1. This will also become 1. This will also become 1. Okay, it's already 1 is there. Okay, and this will also become 1. So there are so many changes over here. It is carried forward. Now T4 will be like this, Now if we select, in order to build T5, we need to select the 5th row and 5th column. So in the 5th row and 5th column, interestingly, there are all zeros because this points to the vertex E. Vertex E is not connected. Okay, vertex E is connected only from, oh no, here it should be 1 because it is connected from D. It is connected from D. So this then it remains as it is, because if you select a row over here, if you select a column over here, you can draw only horizontal line from this one. All the entries are already 1 because you cannot write none of the vertical lines from over here because all are zeros. Therefore T5 remains to be T4. Okay, therefore this is the matrix, and if we write like this, once again A, B, C, D, E, A, B, C, D, E. Now the meaning is there exists path between A to A. It is not a trivial path. It is not a loop. Anyway, self loop. It is not a self loop. Starting from A, we can come back to A, covering, let us see how many stations we will cover. Okay, we will go back to this. So from A, we can leave and we can go to B, we can go to B, we can come to C, we can come to D, we can come to A. So maximum path lengths are 1, 2, 3, 4. Okay, this number of intermediate vertices happens to be 1, 2, 3. Of course, this is not more than n, not more than n. Including A, it becomes 4. So this is the meaning. And B to D, once again we will see. B to A to D is also connected. B to D is connected. B to D is not by a trivial connection. So B, C, D. There exists two paths. Of course, transitive closure, it would also amount to counting paths. How many paths are there between any two vertices selected at random? Okay, it will answer that question also. Okay, anyway, and we will write the algorithm now. Okay, we will write the algorithm. Okay, we know how to do this anyway. Okay, so the starting matrix, of course this is written in order to save time, implements Warshall's algorithm. Input the adjacency matrix A of the directed graph with n vertices. Output the transitive closure of the graph. Okay, T naught, the starting vertex is the adjacency matrix. It is the adjacency matrix, undoubtedly. So adjacency matrix, once again I repeat, adjacency matrix will just give, it's a Boolean matrix of course, it will just give an indication of direct connectionality between two vertices, between direct connectionality. So it is a primitive connection, of course. It is a trivial connection. But what we seek to find out in Warshall, by applying Warshall's algorithm, is non-primitive connection or non-trivial connection involving several paths in between. Okay, several vertices in between any two vertices, several other vertices, intermediary vertices, not more than n, where n is total number of vertices. So we will start with the for loop. Of course, we will select the kth row and kth column for k equal to 1. This will select the row k 1 to n, not 0 to n, 1 to n. You may have seen that do 1 to n do for, once again, kth, ith, for I 0 to n, for j 0 to n. J is meant for column, I is meant for row, that is selected in the k minus 1th matrix. Of course, k minus 1th matrix. Do. This is our convention, therefore we will write this. Anyway, it's an algorithm. Okay. Now we will write that governing rule. Okay. T of k, the entry that is made in T of k, as far as ith row and jth column is concerned, is equal to T of k minus 1, it will be left as it is, if at all it is already 1 in the previous entry, I comma j, otherwise, or if both are 1, or T of k minus 1, I comma k, and if both of them are 1, and T of k minus 1, k comma j, kth row, jth column. If the entry in the k minus 1th matrix, entry in ith row and kth column, kth row and jth column happens to be 1, then the entire expression will give us 1, and we will just put 1 over here. Okay, the entry will be 1. So we will return finally T of n. This is the transitive closure. Okay, as far as complexity is concerned, this is the logical operation that we are going to do. We solicit either 1 or 0 over here, and this is the only expression. Then it is, you should be guessing here, it is n repetitions are done repeatedly. So this belongs to complexity of n cube. It can be easily proved. There is one operation over here, logical operation, of course. This one repeats n number of times, and this repeats n number of times, and the entire thing repeats n number of times. Therefore the complexity of Warshall's algorithm happens to be n cube. There are several applications, okay, excellent applications that are being implemented in the real world. Okay, reachability questions can be answered by just looking at the transitive closure of a directed graph. Sitting in an AC office, a programmer or a planner will be able to just say whether station A is reachable to station E, let us say, and if at all it is reachable, how many intermediate stations are going to come in the way, or what is the number of paths in between A and C. Okay, if you have more number of paths, rather more than one, then it should be non-trivial only, because if at all there exists only one path between any two vertices, of course the adjacency matrix itself will tell us, will definitely give us the clue. Okay, therefore finding transitive closure, though it's a Boolean matrix, is not just alteration of adjacency matrix. It's a logical alteration, okay, done in a systematical way by making use of overlapping solutions. Okay, as per the dictum of a principle of dynamic programming strategy, right? Finding regular expressions in finite automata, this algorithm is called as Kleene algorithm. Anyway, it has roots in transitive closure relationship. It is optimal routing. To find the optimal routing between any two stations, transitive closure can be used, and fast computations in pathfinder networks can be done with the help of a readily available transitive closure graph. Okay, my dear friends, my dear viewers, we will close this Warshall's algorithm discussion, and we will once again come back and to make us every one of us to understand another famous algorithm called as Floyd's algorithm, which will help us to find shortest path between any two vertices selected at random. All pairs shortest path problem. Okay, this will also come under dynamic programming strategy. So with this we will close this session.